Okay, this is part 2 of the Taylor and Maclaurin series. Hopefully you just got through viewing the graphing, what it looks like graphically when you start adding a bunch of terms to approximate the function. All right, so example 4, let's carry on. Determine the Maclaurin series for the natural log of 1 plus x. So Maclaurin series means it's centered about 0. Find the associated radius of convergence. So we know we're going to be needing some derivatives. F of x is the natural log of 1 plus x. F prime of 0, I'm sorry, we're going to get to the zeros. First, let me take derivatives. F prime of x, F double prime, F triple, to the 4th, to the 5th. Let's have a look at this guy. See what's happening here. All right. So, the derivative of the natural log of x is 1 over 1 plus x times the chain rule, which is just 1 over 1 plus x, or 1 plus x to the negative 1. The derivative of the first derivative, or the second derivative, would be negative 1 plus x to the negative 2. The derivative of this guy would be 2. 1 plus x to the negative 3. Then the fourth derivative would be negative 6. 1 plus x to the negative 4. And then the fifth derivative would be 24. 1 plus x to the negative 5. If you look, we're going 1, 2, 6, 24. 1 factorial, 2 factorial, 3 factorial, 4 factorial. This is the same pattern that's developing in our coefficients. So, if we look at this at f is 0, right? So if we go in here, and maybe I'm just being a little bit lazy, but I'm going to replace all these x's with, we're really interested in finding it at 0. Trying not to shake the table because my camera mount will shake the whole camera. So hopefully that's not making you sick. We'll stick our zeros in there. F of 0. Okay, f of 0. Well, that just ends up being the natural log of 1, which is equal to 0. Okay. F prime of 0, that ends up being 1 over 1, which is 1. This ends up being negative 1 over 1, which is negative 1. This ends up being 2 over 1, which is 2. This ends up being negative 6. This ends up being 24. Or 0 factorial, negative 1 factorial, 2 factorial, negative 3 factorial, 4 factorial. That's what we can think of those as. So, that means our function, the natural log of 1 plus x, is equal to 0 plus the first derivative at 0, which is 1 over 1 factorial x to the 1, plus the second derivative at 0, negative 1 over 2 factorial x squared, plus the third derivative at 0, which is 2, or 2 factorial, it's fine, over, I guess I can put the little factorials on there, or I could call this 0 factorial even if I wanted to, over 3 factorial x to the third, plus the fourth derivative at 0 is negative 3 factorial over 4 factorial x to the fourth, plus 4 factorial over 5 factorial x to the fifth, sorry, and so on. So let's see if we can write our little pattern right here. What can we come up with? Hopefully something awesome. This looks like x minus 1/2 x squared plus, I can cancel out the 2 factorial. I just have a 3 right there. So plus 1/3 x cubed. This is going to simplify down to negative 1/4 x to the fourth, because this is the 3 factorial cancels out, plus 1/5 x to the fifth So if we were going to write this series, this is the sum from n is 0 to infinity, -1 because of this alternating stuff, to the n, that will give me a positive start, x to the n over n plus 1. If I'm starting at 0, I need this to be n plus 1 over n plus 1. Let me see if I like that. I can write it that way, but I can also write it as, if I wanted to start it at 1. So if I want to start it as 1, n would be equal to 1 to infinity. This would be -1 to the n minus 1, x to the n over n. This is equivalent. That's another way to write it, and I think this is more standard. Oh, I need to start it at 1. Why do I need to start it at 1? Oh, well, it was okay because I had the plus 1. No, it was legal. I started at 1 if I'm going to have an n down here. I have to have an n plus 1 if I'm starting at 0, so that I'm never dividing by 0. Either one of those works, but I think this is more standard for this function. So, here we go. Let's find the radius of convergence. The limit as n goes to infinity of a sub n plus 1. So, I'll do this one. -1 to the n plus 1. It's just going to be n because of that minus 1. X to the n plus 1 over n plus 1 times, or divided by, I'll go ahead and do the division, divided by -1 to the n minus 1, x to the n over n. So what's going to happen with the absolute values and the negative ones is these can be disregarded, and so this is the limit as n goes to infinity of the absolute value of x to the n plus 1 over n plus 1 times n over x to the n. What can we do with this? With the x's, I can have that, just one x right there. So this becomes the limit as n goes to infinity of the absolute value of x times n over n plus 1. The x is not involved in the limit. There's no n in it. So if I wanted to put it in front, that would be fine. The absolute value of x times the limit as n goes to infinity of n over n plus 1. We could use L'Hopital's rule because this is an indefinite form, or we could use other methods, but whichever method we use, we will come up with the limit as n goes to infinity of n over n plus 1 is 1. And so this is what our limit goes to. So we do get it converging to this value. As long as this value is less than 1, it will converge. If it's greater than or equal to 1, it will diverge. So our radius of convergence is 1, and our interval of convergence is -1 to 1. All right. We just have a few more examples. Example 5. We have done a few Maclaurin series. Now we're going to do a Taylor series. And the Taylor series that we're going to do is going to be centered not at 5. So something not centered at 0 is a Taylor series. In fact, we couldn't even center this one at 0 because we'd be dividing by 0 and that is undefined. So we got to do something. We can write it, though, at a different place. So let's see. At 5, this will work. So let's begin with our function. F of x is 1 over x. Or I'll write x -1. So then f prime of x, double prime of x, triple prime of x, fourth, fifth. All right. This is going to be negative x to the -2. 2x to the -3, -6, x to the -4, 24, x to the -5, -1, 20, x to the -6. Hopefully you're starting to recognize this pattern of 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, and so on. So this is what we're seeing here. Now, what, if it's centered at A, what is f of A? Okay, well, f of A, is 5. So what is f of 5? Let me start there. F of 5 is going to be 1 over 5. And f prime of 5 is going to be negative 1 over 5 squared. And f double prime at 5, triple prime at 5, fourth at 5, fifth derivative at 5 is going to be 2 over 5 cubed. This is going to be negative 6 over 5 to the 4th. This is going to be positive 24 over 5 to the 5. This is going to be negative 120 over 5 to the 6th. Okay, and that's what those end up being. Now let's write the series representation. 1 over x centered at 5 is equal to f of 5, 1/5, plus f prime of 5 over 1. F prime of 5 over 1 is negative 1 over 5 squared times x minus 5 to the first power, plus the second derivative of 5, 2 over 5 cubed divided by 2 factorial, this is really over 1 factorial, times x minus 5 to the second, plus 2 over, no not 2, negative 6 over 5 to the 4th over 3 factorial x minus 5 to the 3rd, plus 24 over 5 to the 5th over 4 factorial times x minus 5 to the 4th, and so on. Okay, this negative 6 is the same thing as negative 3 factorial. This 24 is the same thing as 4 factorial. That's going to help us see what's canceling out. So really what we have is 1 over 5 minus 1 over 5 squared, x minus 5 to the 1. This 2 will cancel here, so we have plus 1 over 5 to the 3rd, x minus 5 squared. Then we have a minus, but the factorials will cancel, minus 1 over 5 to the 4th, x minus 5 to the 3rd, plus 1 over 5 to the 5th, x minus 5 to the 4th, and so on. All right, pretty good. Let's write this. This is the sum as n front goes to 0 to infinity. We have this negative 1 thing going. Let's let it go to the end. The first term will be positive. It's going to be 1 over 5 to the n plus 1 times x minus 5 to the n. I think that's going to do it. Let me check. Yes, I like that. So if we find the associated radius of convergence, then what can we do there? Well, we can do the ratio test. The limit as n goes to infinity of all of this stuff. Negative 1 to the n plus 1. X minus 5 to the n plus 1. Over 5 to the n plus 1 plus 1. Over negative 1 to the n, x minus 5 to the n, over 5 to the n plus 1. Alrighty then. This is going to equal to, so this is my problem being continued. Okay. I shouldn't have made that go in because I'm going to need that room. Alright. What's going to happen here? This is going to equal to the limit as n goes to infinity of the absolute value. Okay, the negative ones can be disregarded at this point. X minus 5 to the n plus 1 over 5 to the n plus 2 times 5 to the n plus 1 over x minus 5 to the n in the denominator. What's going to happen here? This will cancel, and I'm left with the x minus 5 here. 5 to the n plus 1, this will cancel and I'm left with a 5. So it becomes the limit as n goes to infinity of the absolute value of x minus 5 over 5. There's no n in this equation, in this expression. So the limit has no bearing. We just are looking at this is what it converges to. The absolute value of x minus 5, and I don't need to even put the 5 in absolute values, just the numerator really. As long as this is less than 1, we're in good shape. If you multiply this by 5, as long as this is the absolute value of x minus 5 is less than 5, we're in good shape. We can remove the absolute value signs and we get x minus 5 is less than 5, add 5. This is our interval of convergence, and the radius of convergence is 5. And that is what we have for that one. These last two examples are fairly short. Let's see. Determine the Maclaurin series for f of x is the cosine of pi x over 2. Well, we have already done some pretty good work where we figured out that if you had the function cosine of x, we could represent this guy as the sum from n is 0 to infinity of negative 1 to the n x to the 2n all over 2n factorial. All right, that's what that could be. So this is basically a transformation of this. Instead of x, we have pi x over 2. So our series for this, for f of x, is the cosine of pi x over 2, would just be the sum from n is 0 to infinity of negative 1 to the n. Instead of x to the 2n, we have pi x over 2 to the 2n over 2n factorial. And you can do that. Let's look at example 7. Determine the Maclaurin series for f of x is x cubed times the natural log of 1 plus x to the 4th. We have not developed this, but what we have already developed is the Maclaurin series representation for the natural log of 1 plus x, which is equal to the sum from n is 1 to infinity of negative 1 to the n minus 1, x to the n over n. So we did this just a couple of examples ago, and so we have this going for us. This is a bit of a transformation. Let's see, this function is x cubed times this, and it's not x, it's x to the 4th. So let's do the same thing that kind of we did in example 6. Let's see, what would the natural log of 1 plus x to the 4th be represented as? It would be represented as, from n is 1 to infinity, negative 1 to the n minus 1. Instead of x, we're going to put in x to the 4th, to the n over n. So that would be 1 to infinity, negative 1 to the n minus 1, x to the 4n over n. All right, that's this. But it had more. It had this x cubed, so we can fix that. Let's multiply this x cubed, the natural log of 1 plus x to the 4th, would simply be x cubed times n is 1 to infinity of negative 1 to the n minus 1, x to the 4n over n. Well, we can bring this x inside of here, and so this would be x to the 4n times x to the 3rd, and common bases, their exponents that are being multiplied, their exponents combined through addition, so this can be written as n is 1 to infinity of negative 1 to the n minus 1, x to the 4n plus 3 all over n. And that's how we can write the Maclaurin series representation for this function. So these are some techniques we can use to write it for more than just a few functions, but for many other functions.